Okay, so now the recording. All right, so we are week 6. We are over the halfway point. Today we're going to be doing the normalization group. So let's just remind ourselves what we did last time. So last time we continued Kadanow's block spin ideas, and we extended them to look at correlations. And so we spent a bit of time talking about scaling laws in correlations, in correlation functions. In particular, what we discussed was how the two-point correlation function, after you've done a coarse graining by a scale L, relates to the correlation function at the microscopic scale. And after some calculations and so on, we obtained the formula shown over here. And from this, we were able to then beat it down, sort of reversing the side of it to this form over here. So this in fact is the scaling form for the two-point correlation function. So if I'm taking measurement of the correlation function using neutron scattering or X-rays or something like that as a function of reduced temperature T and external magnetic field for two correlation function between 2 points separated by a distance r, that scales by r to the power r times t, the reduced temperature, to this exponent 1 over y sub t times h times t to the power minus yh over yt. And we derived those scaling forms in the lecture, and there's a prefactor in front which is distance dependent, and that goes as 1 over r to the power d minus yh. Now this was a very important result that we obtained because it enabled us to really interpret what these exponents y sub t and y sub h are. So just so you remember, when Kadanoff introduced his idea of coarse graining, he didn't know how the temperature and the effective field would transform, and so he guessed that as a function of the scale L that you're making your coarse graining with, he guessed that they would scale as some power laws, and he called those different exponents y sub t and y sub h. And he turned out to be correct. His guess was in fact right. And now we can see the physical interpretation of those exponents. So the fact that the scaling function here scales with r t over 1 over y sub t, well, that must mean that it scales as r over the correlation length in physical units. And so we can read off then that the correlation length scales as a t to minus nu. That's how it should scale. And so that means that this exponent 1 over y sub t is actually the inverse of the correlation length exponent nu. So it actually is something physical that we can measure. And then I also showed you that we can write the scaling form as shown over down here at the bottom in purple. And this we expect the correlation function to scale as a new critical exponent eta, and that critical exponent is defined down here. It tells us how correlations vary with distance or with wave number once you take the Fourier transform when you're exactly at the critical point. Exactly at the critical point, the system is self-similar. All the correlations decay as power laws. The system is a fractal, and the critical exponent that tells you about the fractality of the system is called eta. And when I take the back Fourier transform into real space, then I get this factor over here at the front, and that factor over there, then we can identify with the exponent y sub h. So the interpretation of the exponent y sub h comes from that analysis. Okay, so that's what we did last time. And we derived some scaling laws as well, which I'm not going to go over. So today we are going to start on the normalization group. And so our goal now is to follow section 9.2 of my book on the basic ideas of the normalization group. And so what our goal is as follows. First of all, we're going to introduce a very general and pretentious formalism that will basically describe how Hamiltonians as a function of scale vary in Hamiltonian space. Let's just unpack that. We're going to think of scale as like some effective time. And what we're going to do is we're going to see that as we coarse grain a system, what that does is it means that the Hamiltonian flows in an infinite dimensional Hamiltonian space. So what we're going to be doing is we're going to be constructing a dynamical system theory of how Hamiltonians transform in Hamiltonian space. So this is a dynamical systems theory. For Hamiltonians. So that's the first thing that we're going to do in it, and it will seem very pretentious, and you might say, well, what use is it? So what we're going to see is that this will enable us to understand where the Kadanoff assumptions come from. Actually, it's going to do more than that. Let me just be a bit more precise about what it says about the Kadanoff assumptions. Is that assumption number one, that assumption was that after coarse graining, the coarse-grained Hamiltonian is same form as the original Hamiltonian. That was Kadanoff's great idea. We use that to say that the free energy of the system is then the same function of the coarse-grained system as it is of the original system. This assumption is wrong, okay? So this assumption we're going to see is not correct. And in fact, we're going to see that when you coarse grain, you don't get back the original Hamiltonian. You get something different. And that fact that you get something different is why we think of it as in Hamiltonian space. The Hamiltonian is then executing a trajectory as you coarse grain the system. So that's assumption number one is not correct, but we get something better. Okay, so that's the first thing. And then the second thing we're going to see is that assumption number two, his assumption about the parallel scaling, that assumption that T L is equal to T L to the Y sub T, etc. So that assumption is correct. And we're going to see why. And we're going to understand that. So that's what we're going to get out of the renormalization group. But we're going to get more. So we're also going to get that we have because the dynamical systems picture gives a new concept, and that new concept is the idea of a fixed point. So in dynamical systems theory, you have a flow in some phase space of a dynamical system described by, say, Liouville's equation, which is equivalent to Hamilton's equation of motion. And the system will keep going until eventually it will hit some fixed point. Okay, it might never hit a fixed point. It might just be chaotic, but sometimes it'll hit some fixed point. And we're going to see that in the normalization group, there are fixed points, and those fixed points have a physical significance. So these fixed points we will see have a physical significance. And moreover, when we get to the fixed points, these fixed points control the values of the critical exponents. So even though we can calculate we can literally calculate the critical exponents, and the reason we can do that is because we've removed what was a convenient assumption for Kadanoff, which turned out, in fact, to be wrong, but we replaced it with something that is better. Okay, so that's the basic idea. So let's be a bit more precise. Yes. I don't know if you were here. Were you here last lecture?
Yeah.
Were you here at the previous lecture?
Yes.
There's one lecture where I think you weren't here. Maybe that's what I'm thinking.
I wasn't here.
Okay, I'm not sure. So, okay, well, apologies then. But what do you mean define it more precisely? Remember, here two assumptions. One assumption was that the functional form. Remember, we discussed how as you coarse grain, the system appears to be further away from TC.
Yeah, I was asking the second one. I think I'm just maybe I need to reread it.
No. Remember what we did was we saw that as you coarse grain, you move further away from TC because the correlation length has got smaller. When the correlation length has got smaller, that means you're further away from TC. Okay, so that means the relative temperature, T minus TC over TC, after I've done a coarse graining, is now bigger than it was before because you're further away from TC. How much bigger? Well, what Kasloff assumed was that after one coarse graining, you're now the original temperature T times a distance that depends on how big the coarse graining scale was, L to the power y sub t. And we define that exponent y sub t. Okay. Does this bring it back?
Yeah, that makes sense.
All right. Okay. All right. So let's have a look at what we mean. So we're going to relax the approximation that we had before, that the form of the coarse grained Hamiltonian was the same as the original Hamiltonian, which I'll write as the coarse graining scale 1. So we have the approximation that HL is equal to H1, meaning i.e. has the same functional form. So how are we going to do that? So we can write, so first of all, I'm going to make a slight change of notation. So I want you to be nimble and aware of this. So sometimes I will talk about the Hamiltonian, and sometimes I will say, well, it's easier just to talk about minus beta times the Hamiltonian. So usually from now on, I'm going to be, when I talk about the Hamiltonian, I will talk about, I will really mean what is minus beta times the original Hamiltonian, because I don't want to keep writing factors of minus beta throughout all the formulas for the rest of the quarter. So that's the first thing. So I'll try to remind you about that. Now, what we are going to write as the Hamiltonian is as before. We can write it as a sum of terms with the coupling constants, then times these operators theta n, which are local operators of the underlying degrees of freedom. And I will use the notation that these underlying degrees of freedom are spin variables, but they don't have to be. Okay, this formalism can be used for anything. Okay, but we'll just pretend for now that they can be used, that we can use the notation that they're spin variables. So these things here are the coupling constants. And these things here are local operators of the degrees of freedom. Which I'm going to write with a symbol S sub I. Now, what you might assume is that if you start, for example, with say a nearest neighbor Ising model, then K nearest neighbor will be non-zero, and the coupling constant for any other interaction is equal to 0. That's what you would say. So you just say that the Hamiltonian is just minus J sum over nearest neighbors, SI, SJ. That would be your Hamiltonian. And Kadanoff's assumption was that if you started with this, then under coarse graining, you would end up with this as well. So Kadanoff, his assumption number 1 was that after coarse graining, the Hamiltonian, which we'll call H sub L, has the same form. Okay. But now we're going to relax that assumption. So what we're going to say is the following: that as we change scale, how do all the coupling constants change? So we're going to say that you might have started off with, just the nearest neighbor coupling constant being non-zero. But as I coarse grain, now we're going to allow the possibility that you could have next nearest neighbor interactions, and next nearest neighbor interactions, and next nearest neighbor interactions, and so on. So we're going to allow, in principle, for coupling constants that were 0, originally were 0, to become non-zero when we coarse grain. So we can draw a kind of schematic picture of what that might look like. So let's suppose I'm going to draw a high dimensional space here. It's really an infinite dimensional space. I can't really draw it properly, so you're just going to have to use your imagination. And so on and so forth. So this is coupling constant space. So what do I mean by coupling constant space? So what I mean is you enumerate all possible local operators. So they may be, for example, SI, SJ, sum over nearest neighbors. That could be one of them. Then there could be sum over I, J, K, SI, SJ, SK. There could be sum over SI, sum over S, I don't know, I plus N, where N is some vector a long way away. So it could be a function of distance, for example, and so on and so forth. So I can write down many, many things. There's an infinite number of these things. So each of those local operators has a coefficient, which will be, let's say, K1, K2, K196, and so on and so forth. So then what if I tell you, well, here is my system, it's represented by a point in this space. So a point in this space represents a particular Hamiltonian with a specific value of the coupling constants. And it may be that some of those values are zero. Some of them will be non-zero. But in general, there'll be a point in this space represents a Hamiltonian. Just like when we do phase space, we write down a phase space, its axes are 6 n-dimensional. I've got n particles, 3 coordinates, 3 velocities, 3 momenta. And so I have a 6 n-dimensional space. A point in that space represents the state of the system, particle, all the particles and all their momenta, and then as the system evolves in time, it traces out a trajectory in phase space. So similarly, now I have my physical system described by a Hamiltonian. Now, as I coarse grain, I generate some trajectory in this space, or something like this. So the idea is that coarse graining changes the coupling constants. And repeated coarse graining sweeps out a trajectory in coupling constant space, or in a Hamiltonian space, I should say. So that is our picture. So in some sense, then the time variable in this dynamical system picture is really the scale of coarse graining. So why is that? Well, so the first time step is I coarse grain by L. That's my block spin size. Time step number 2, I coarse grain again. What's time step number N? I've coarse grained again by L. And once I've got, say, to this level, what is my length scale? So now I've coarse grained by L times L times L times L all the way up to N of these things. So this is equal to L to the N. So the number of time steps actually tells me the scale I've got to is L to the N. So then we can think of the total time is I can think of this tau is L to the N. So the logarithm of this time is equal to n log L. So in other words, the effective time variable is not L itself, but related to the logarithm of scale. So we'll see that formally later. Okay, so that's the basic idea. So if I know the scale that I'm at, so this is the scale, then how many intervals have I done? So what I've done is the number of time steps is scaling like the logarithm of the scale that I have reached at that time. So we're going to see that this is what the time scale looks like. Okay, so that is our picture. So let's now explain a bit more how we formulate it. So we're going to do so the normalization group has two ingredients. So the first one in step one is we have to concretely construct Haslov's block spin picture. And then step two, we're going to see that the origin of singular behavior comes from an infinite number of repetitions of a renormalization group transformation. So that's what's going to happen. Now let's discuss what step one looks like. So in step one, we sometimes talk about this as elimination of degrees of freedom. So do you remember last lecture, we talked about the Fourier components of the coarse-grained magnetization. So if we look at the coarse-grained magnetization, on scale lambda. So what I've done is I've taken my physical system, I have spins on my lattice like this, and then I've constructed some block spin, maybe something like this. So there's my block spin with dimensions LA, like that. So this block spin, the block spin has no Fourier components. With wave number k greater than the coarse graining scale lambda. So I've got my coarse graining scale lambda, which is L over A. So now any configuration information on a scale within the block. Now that we've replaced all the spins in the block by just one representative spin, we can't see what was in the block in the first place. So we have no Fourier components on the scale larger, on a wave number larger than 2 pi over lambda. So we can think of this as being that we've eliminated degrees of freedom. So this is eliminating large wave numbers. And there's a formal way that we do this, and in fact, later in the course, I'll show you that you can do this using Feynman diagrams. But for now, we don't need to. I'm not going to go into that, but I just want you to have the idea that this picture is an elimination of degrees of freedom. Okay, so what we think of then is that the renormalization group is a map from my original degrees of freedom k. Let me just write it like that, to new coupling constants k prime. So I'm just going to write this in a very formal way. All my coupling constants, which I can think of as one big vector, are just some non-linear transformation of what they were on the previous step. And so this is the RG transformation at scale L. So I've coarse-grained by L, and this L must be greater than 1 because we're lumping together microscopic degrees of freedom. So a block spin has L obviously greater than 1, and by coarse graining this, what we are doing is making a many to 1 map. So let's see why. So let's suppose I were to draw one of a configuration like this. So here's my system. I've got a bunch of spins. I'm just drawing this in 1D just to make it easy. So now what I'm doing is, let's suppose I'm taking a configuration like this. I'm coarse graining them in groups of 3s. And so this is my block spin. And now if I were to look at what the coarse-grained version looks like, so this is microscopic. So now this is coarse-grained. So what I'm going to have is something like this. Let's say that my rule is, if I got in this block, I've got 2 spins point up and 1 spin point down. So we'll say that the effective spin then is just pointing up. And then I can say, let's take the next spin, the next block. So here's the next block. And in that one, well, unfortunately, it's the same thing. In that one, there's more spins pointing up than pointing down. Let's suppose in this one over here, I had a spin pointing down like that. Then once I look at this block spin, then I'm going to see there's more pointing down than up. And so this one would be replaced by a down spin. So this is just a picture, and this particular map is the majority rule map. Have a block size that gives you an odd number of microscopic spins and then if more are up, then the block spin is equal to up, and if more are down, then the block spin is replaced by down. So that's an example of a coarse graining renormalization group. Now, one thing that you can see is that why do I say that this process is a many-to-one process? Well, suppose if we look at, say, look at block number 2. So here's block number 1, number 2, number 3, and so on and so forth. Let's look at block number 2. So that has got 2 spins pointing up and 1 spin pointing down. That was my block. But if, for example, I had the following: this spin pointing up, this one pointing down, this one pointing down. So that one. Both of these will give you the same picture for the block spin. So this is microscopic configuration number 1, microscopic configuration number 2, and they have the same block spin, so they have the same, let's use a different color, they have the same macroscopic description. So that's why this map is a many-to-one. There's many microscopic states that correspond to the same coarse-grained states, and the implication of that is that this renormalization group transformation has no inverse. So it's in fact it's not actually a group at all. Groups have to have inverses, so this is not a group. So this means that the normalization group is actually a semigroup. It's half true. Okay, so let's then see what this means. So let's now imagine that we were to do the following experiment. We're going to look at the combined effects of 2 renormalization group transformations. So I'm going to start off with K prime is defined as the renormalization group transformation by an amount of L1 acting on some coupling constants. And then I'm going to look at what happens if I then define K double prime to be RL2 acting on K prime. So I first of all coarse grain by L1, then I coarse grain by L2. So this then is the coarse graining of L2 acting on the coarse graining operator on L1 acting on my original coupling constants K. And so this then, what is this? Well, by doing this, what I've done is I've overall, we've transformed by L1 times L2. Coarse grain by a scale L1, done by a scale L2. So the overall scale is the product of L1, L2. So now I have an equation that says L1, L2 of R acting on K is the same thing as the transformation acting on L2 times the transformation acting on L1 acting on K. So this equation is a fundamental normalization group equation, and that will tell us, in fact, this equation will turn out to be the origin of a parallel scaling. So so this will turn out. In fact, this is where Kazanoff's second assumption comes from. So now you can ask, well, what happens to the partition function? So do I really want to explain this? Yeah, I guess I should. Okay. Yeah.
Yes. Like the order doesn't matter.
Yeah, they commute.
Is that something that we can from this or?
Yes, because it's the same transformation, but just with a different scale factor.
So I guess if we're thinking about postgrading these things, then we could do that. Yeah, I guess try to work it out that it shouldn't matter.
Yeah, well, I'm kind of about to show you exactly how that works. Okay, so you're right to ask this question. So let's step back from this now and ask, well, what happens to the partition function when we do coarse graining? Okay, so we've defined this this calculation, this coarse graining, and the Hamiltonian evolves in the space of Hamiltonians, all stuff like that. What's going to happen to the partition function? So anybody want to guess what happens to it? It gets smaller. Okay, there's one answer. Yeah. Anybody else got an opinion? Anybody want to say it gets bigger?
Should it scale with course
So you're saying it should scale with the coarse graining size, so therefore it would get bigger because we're coarse graining to a bigger length scale.
like inverse.
You what?
Like inverse scale.
Inverse scaling. You know, it's going to get smaller, like the correlation, for example. Okay. So you said it was going to get bigger, and you said it was going to get smaller. Anybody else got any other suggestions? Those of you who are sitting next to somebody, take 30 seconds and discuss with your neighbor. If you're not sitting next to somebody, go and just jump forward and discuss with the person in front of you. So literally, break up into groups of 2, dimerize, one group of 3 if you want to talk with those guys. You're at the back. If you want to go in. So would you want to come and talk with this guy? This person? Him? So introduce yourselves, say hi. Okay. And so do you think the partition function is going to get bigger, or do you think it's going to get smaller? That's what you guys have got to discuss. And you can introduce yourselves first.
If it's just one block, then it becomes like whatever. I feel like it's my intuition is that it's smaller. The number of spaces is smaller. Yeah. Because like when you do when it's like scale that it's just like too much scale and you scale like the entire. Oh, I see what you're saying. Yeah. Oh, that's becomes just like like the trade is gonna be recognizing all negative.
Okay, so are you converging? Converging? Do you have a solution? Have you guys decided what's happening? Yeah, okay.
But if you make it happen, you're still making.
You're bigger, you're smaller.
No, I also think it's.
It depends on how, if they're two guys smaller, okay? Smaller, what did you guys? Depends on what. Also smaller, is it the group of 3 at the back? So everybody else here supposed to be smaller. So what do you guys think? Smaller or bigger? Alright. So the group at the back says this it's going to get bigger, and then these 3 groups think it's going to be smaller. So if we were doing science by democracy, we would have voted for it to be smaller. None of you are right. Okay, it doesn't change.
So an average.
No, you're not. You're not even right on average. Maybe geometric average or something like this. It doesn't change. Okay, so let's think about why it doesn't change, and then I'm going to prove it to you mathematically. Okay. The Hamiltonian changed. Yes, the Hamiltonian did change. That's completely right. The Hamiltonian, you're right to be surprised. The Hamiltonian changed. How come the partition function doesn't change? The point is that the variables that you're summing over also changed. Okay, if you think of the partition function as being like an integral, after you've done the coarse graining, you've changed the Hamiltonian. But now you've got to look at the change in the measure. You've got to look at the integral dx, how does that change? And those 2 things precisely cancel out. Okay, the reason they cancel out is that when we're coarse graining, there's no physical coarse graining going on. I still have just a bunch of spins sitting there, flipping, going up and down like that. All I've done is I've decided, okay, for purposes of doing statistical mechanics, I'm going to group these ones into one box, these ones into another box, these ones into another box. These are now the new variables. So those new variables have their own dx, their own measure, their own summation over their values. And so all I've done is change the order in which I do the sums in the partition function, but I haven't changed the total number of degrees of freedom in the system. Okay, so it doesn't change. So let me show you. And I'm delighted, by the way, at the outcome of this pedagogical experiment, because now you're all really interested to know how the heck can this possibly be true. Okay, so this is great. So let's have a look and see what happens. So let's see how this works. So I'm going to define the partition function of n spins. So I'm going to call it Zn, and it's going to depend on all the coupling constants, whatever they are, and it's the trace of e to the h. Okay, now remember, my h is really what we used to call minus beta h. So I've absorbed the factor of minus 1 over kt c into this just to make it easy, and then I'm going to define the free energy per degree of freedom to be, I'll call that G, and that's 1 over n times the logarithm of Zn. Okay, so having got rid of all these annoying factors of kt makes the equations a little bit easier. So what does RL do? So when I do my renormalization group transformation, it reduces the number of degrees of freedom by a factor L to the D. And we saw that last lecture. So after I've done one renormalization group transformation, I now have a new number of the new degrees of freedom, and that is n over L to the D. And so my new coarse-grained variables, which I called SI with a capital I, after I've done the transformation, this I goes from 1 up to n prime, not to the original number. So that's the first thing. And then the Hamiltonian is now the Hamiltonian which has been transformed under the RG transformation, but it's now a Hamiltonian not of n degrees of freedom, but of n prime degrees of freedom. And those n prime degrees of freedom are the SI prime. Okay, so how did we construct this? So how do we construct this? So what I'm going to do is I'm going to say the following. I'm going to first of all define on the left-hand side e to the h n prime as a function of the new variables k prime and the new spin variables si prime. And how did I get that? Well, I started with my original Hamiltonian, which had n degrees of freedom, and it had variables k and si, like that. And then what I did to get this effective Hamiltonian was I coarse-grained, and we've talked about coarse-graining before. What I was doing was I was taking a trace over my SIs, but I wasn't doing the same trace that I do in statistical mechanics. We talked a lecture ago about the cartoon picture of this, but now I'm going to say it in a more formal way. So notice that when I'm writing this equation here, this equation depends on SI prime. That's defined on the left-hand side. So the game is, you tell me what is my coarse-grained configuration, my configuration of the block spins. Okay, that's what I mean by SI prime. I want to know what is the Hamiltonian for that. And how did I get that? Well, we saw that in this picture over here. We summed over all possible microscopic states of the system and I showed you an example over here on the left-hand side, to get every coarse-grained variable. So in other words, the game is this. You tell me a macroscopic configuration. The macroscopic configuration that we had over here was this one, the one over here on the left-hand side. Spin down, spin up, spin up. I drew for you one possible microscopic configuration that was consistent with that. The ones are above it in the blue boxes. But as I just showed you, there were many microscopic configurations that would give the second block spin pointing up. There are many microscopic configurations that would give me the second block spin pointing, first one pointing down. There are many microscopic configurations that give me the third spin pointing up, and so on. And so what we can say is that we're going to sum over the SIs, but we're only going to sum over microscopic configurations that are consistent with the specified coarse-grained configuration. And what is that specified coarse-grained configuration? Well, that specified coarse-grained configuration is exactly this. It's actually SI prime. So I'm now doing a partial sum. So over configurations that are consistent with this specified coarse-grained one. And then this over here on the left-hand side, this then is the effective Hamiltonian on scale L, which is greater than 1. So just as I promised you, what we are doing by coarse graining is we are eliminating degrees of freedom. We eliminated the microscopic configurations in order to get our block spin. And so we had to do a partial trace over all of those degrees of freedom. Okay, so now I've got this effective Hamiltonian. So then you might say, well, fine. So how is this effective degree of freedom, this effective Hamiltonian related to the thermodynamics? Well, our answer is this. Suppose I just gave you the effective Hamiltonian at scale L plus 1, L minus 1, sorry, L greater than 1, then what you would say is, well, if I want to know what is the Helmholtz free energy of the system, so what do? Well, I take my Hamiltonian, my Boltzmann factor, and we know that this came from doing a coarse graining, but let's suppose we didn't know that. So I said, here's my Hamiltonian. It's got n prime degrees of freedom. Their name is SI, capital SI prime. And then I just take the trace over all of those. And that would give me, if I did the unrestricted trace, that would give me all of the statistical mechanics of the system. So I can say that once I do this, the second trace now over the new degrees of freedom, I'm going to get the same e to the minus free energy over kt, the same partition function. So let's see this in a more formal way. So there's a way to say this. We can write this formally using the language of projection operators. don't, if you're worried about this being very formal and you're thinking, oh, it's going to be like quantum mechanics, it is in some sense, but we're not going to use it, this language, other than just what I'm going to show you right now. So what we could say then, we're going to write it in the following way, that my rule for doing coarse graining, for getting my coarse grained Hamiltonian, that depends on my new coupling constants and my new degrees of freedom, SI prime, is that I take my original Hamiltonian, like so, and then what I'm going to say is we are going to still take a trace over the microscopic degrees of freedom, like so, the SIs. But what I'm going to do is I'm going to put in here a projection operator, which I'm going to call P of little si prime, like so. And what this thing does is the following. If you tell me what is this si prime on the left-hand side, so this is specified over here, and then this operator, this projection operator, will give me 0 if the microscopic configurations are consistent with the specified coarse grain configuration Si prime, and it'll equal 1. Sorry, I said it the wrong way around. And it will equal 0 if not. So that's just a formal way of saying it. So let me give you an example, just so you can see that it's not just some mumbo jumbo. So let's take an example. I'm going to suppose I've got Ising spins on a lattice with spacing A. And I'm going to have my RG transformation is some R of L, but I'm going to say that the block spins (2L plus 1 times A). So you tell me what L is, whatever, any integer you want. And then my blocks are 2L plus 1 in linear dimension, in whatever dimension I have. So this means that there are an odd number of spins in the block. Okay, so then I'm going to define my block spin variable. So we're going to do majority rule, just as we did in our simple example before. So I'm going to say that Si prime is equal to the sign Sign, not the trigonometric thing. I take all the microscopic spins in my block I and add them up, and I'm going to get a number, and I just look at its sign. So if it's this is guaranteed to be just plus or minus 1. So this is another way to make a block spin construction. Then I can write down my projection operator. Is just this, P of Si prime. So this is going to be the following. You tell me what the SIs are, and then I do the coarse graining. So what do? I define a delta function of Si prime minus the sine of the sum of I in the big block I, Si, like that. And then I product this over all the spins Si. So this delta function, this is a Kronecker delta. So this thing is going to tell me, it'll give me 0. This delta function will be 0 if I sum over and I don't get the value I want, and if I do get the value, then I get 1. So only microscopic configurations little si that give rise to the desired coarse-grained configuration give me a value p is equal to 1. Okay, so let's have a look at what are the properties of this projection operator. So the first property is pretty obvious, that P of Si prime is greater than or equal to 0. So that's the first one. The second property is that P reflects the symmetries of the original Hamiltonian. So in our particular case, we have a Hamiltonian where there's a symmetry between spins up and spins down. The same thing will be true with this projection operator. So it's symmetric under all the spins going to minus and plus. And then the third thing is that if I take the sum over all possible coarse-grained configurations of P of Si prime, then that is equal to 1. So those are the properties. So let's just see where they come from. They're fairly obvious, but let's just make sure. So property 1, that follows because when I compute e to the h prime, the transformed Hamiltonian, that has to be greater than or equal to 0, because the exponential of anything is greater than or equal to 0. And so then I can take the log, and then that gives me that that p is greater than or equal to 0. So that's the first thing. So seems very formal. And then the next property is that if I write down my Hamiltonian as something like this, whatever, then when I coarse grain it, I'm going to get n prime k naught prime plus h prime sum over I si prime plus k1 prime sum over I and j si sj plus k2 prime sum over I, j, k, si, sj, sk, and so on and so forth. So I have the same form, but different values of the k prime. So that's the that's why whatever I have, since I've got every possible interaction you can think of in there, every interaction in there that is allowed by symmetry is present in the original one, so it'll be there in the next one. Now let's ask what happens to the partition function. So the partition function is Zn prime of k prime. So this is the trace of over the coarse grained degrees of freedom of e to the h n prime k prime si prime. So that's what it means. And I can write this as the trace over the si prime. And in this thing, the original, this part over here, well, this we can get from the equation over here on the left-hand side. So this then is the trace over the microscopic degrees of freedom, Si, P of Si prime, e to the h n k Si. So that's just writing in what we had on the previous page. And then I can swap round the order of summation. So this then is the trace over the microscopic degrees of freedom of the trace over the Si like that. I can just swap those round. And then this thing over here, this is this third property. And so this is equal to just the trace over Si of e to the hn, my original Hamiltonian, times 1. And that then is the original Hamiltonian, and therefore the original partition function. Yep.
So it's actually a requirement of the course grading to have the partition function be the same. So if you go back to the requirement at page 123, that's not required. Like if you just start with the system that had this new state variable that was S capital I,
Right.
then you wouldn't need to take into account the multiplicity.
Right. I mean, the fact that all we're doing is we're summing over configurations, and every configure. Another way to say this is this: every configuration that was there microscopically is represent in the partition function, is also represented in the coarse-grained partition function.
By just having that factor.
Because what I've done is I've counted the same number of degrees of freedom. I've just done it in a different way. I first of all took the small degrees of freedom and lumped them into some effective parameters in the Hamiltonian, and then once I'd done that, then I took those larger scale degrees of freedom, and then coarse-grained those all the way up to the system scale. So all we've done in the normalization group is, instead of summing over all the degrees of freedom at once, we first of all summed over small numbers of them, and then we've summed over small numbers of those new variables. So we've done an iteration of successively integrating out degrees of freedom, but in the end of the day, we will have integrated out each degree of freedoms, each configuration of the system will have been counted exactly once. So the crucial step in all of this was this formula here. Okay, this is like you've seen this formula in quantum mechanics. In quantum mechanics, you know that if I have a complete set of states, then that is equal to 1. It's called completeness. It just says I can take my state vector, I can write it in terms of some arbitrary eigenfunctions, and then the sum of those eigenfunctions will just sum up to 1. So this is just, so all this is saying is, if I sum over every possible coarse-grained configuration of the system, all I'm going to end up with is just 1. And that's what the projection operator is doing. And you can verify it over here. Okay, well, we're out of time, so we've got to the point where I wanted to, pretty much where I wanted to get to. Next time, I want to talk a bit more about the trajectories in Hamiltonian space, and in particular, where those trajectories have to end up, and what is the physical significance of those trajectories. Okay, so that's it for today. So I can take questions outside.